Okay, okay, okay. Good evening. Welcome to the next live session. I'm just writing down the topics that we discussed. We first discussed in fact, the self-phase modulation we had discussed the previous week. We discussed cross-phase modulation. We also discussed the scattering phenomena, uh, which are also nonlinear processes. And we discussed in detail Raman scattering and Brillouin scattering. Um, Raman scattering, as we discussed, could be used for making amplifiers, which are useful for communication systems. But Brillouin scattering is typically considered a deterrent for optical communication systems. And after that, we discussed the working principle of some of the commonly used components which are used to build the fiber optic network. So we are slowly moving into the networks, and the components we discussed: variable attenuator, how a polarizer works, and we also discussed how polarization controllers work. Uh, then we were uh, looking at very important component, isolators, again polarization independent isolators, then circulators. Uh, then we also discussed wavelength filters, circulators and isolators. We also talked about polarization insensitive operation, which means it will work as a circulator or isolator for both the polarizations. Then, along with wavelength filters, we discussed one of the most commonly used devices these days, which is um, arrayed waveguide grating. Uh, Waveguide grating, and then this device called as wavelength selective switch, WSS, which is based on a semiconductor, which is based on SLM, spatial light modulator, and so on. So these were the topics, and uh, you can ask your questions if you wish right now. If you have any questions, you can type it in. Um, in assignment, week 10 assignment, there are two corrections. These are typographical errors. Uh, Somebody had pointed out, so I'm just making two corrections. Um, the first correction is in um, question 1. It's not even a correction. You have the data in question 2. For question 1, use A effective as 50 micrometer square. That information is there for question 4, 5, but the same you can use it for question 1 also. The next change is in question 13. We can use the power as 200 microwatt, 200 microwatt instead of 200 milliwatt. And in question, in fact, there are 3 corrections. And the third correction is that um, in question 17, 18, the data for fiber loss, you could use 0.25 dB per kilometer Sorry, this is not in question 17, it is only in question 18. 0.25 dB per kilometer instead of 0.5 dB per kilometer. So these are some corrections which I have sent in announcement also, but please take care of that while you are solving. Um, if you have any questions based on this week's content, you please ask here in the chat window. As usual, otherwise what I will start doing is I will start discussing the approach to solve the assignments and come back to your questions at the later point. So, in fact, questions 1, 2, 3, 4 are all very, very formula based. Question 1 says, the data for question 1 says your Raman gain coefficient is given, Brillouin gain coefficient SBS is given to you, length is given to you, alpha is given to you, lambda is given to you. Okay. Now you are asked to find SRS threshold, SBS threshold. In the meantime, I'm seeing a question here in the chat window. Let me answer that first. What is the effect of backscattered light over the modulated light forward? So actually, it does not affect the modulated light at all. In the transmission, the transmitted light will so to answer that question, so if you remember, we discussed this in class that as a function of input power, if you look at reflected power, this is the Stokes power, which is the reflected power, and wherever this, so this is the threshold at which this process, this is your SBS threshold, and corresponding to the SBS threshold, your transmitted, so this is power. I'm also plotting transmitted power starts saturating. So what is the influence? So this red line shows heat transmitted. So beyond the Brillouin threshold, what really happens is, as you increase the input power, the transmitted power does not increase, it will actually saturate. So that is the influence of Brillouin scattering in the forward direction. Beyond the threshold, when you increase the input power, the transmitted power, instead of increasing, it gets clamped because all the power gets reflected. Is SBS bidirectional like SRS? No, SBS is not bidirectional, which is why we discussed in detail about the phase matching condition. We discussed in the lectures that whenever you have pump propagating in the forward direction, you have the gratings, it gets phase matched with the gratings in the forward direction, and the Stokes happens, or the Brillouin shifted frequency is found to travel in the backward direction. It is not bidirectional, right? SBS in a fiber is typically unidirectional. You could have other media where phase matching can happen in other directions. In that case, it could be bidirectional, but in a fiber, it is unidirectional. Like the AAC beats with the signal and creates some noise, will the SBS light beat with the signal and create any noise? Actually, no, because the SBS signal is actually created in the Stokes. That's a very good question. The SBS signal is the unwanted Stokes is appearing in the backward direction, whereas your signal that you want to transmit is appearing in the forward direction. So if you look at the receiver is actually not seeing any Stokes shifted light. So there is no beat noise because of SBS. The Other thing you can have, there is something called as guided acoustic wave Brillouin scattering, which is not taught here. It is because of, so this SBS we discussed in class is because of the longitudinal acoustic modes. Now there could be radial acoustic modes or flexural acoustic modes, which would result in forward scattering, and in advanced coherent communication, one of the fundamental sources of noise is this gobs, which is not really a topic for course, but if you're interested, you can read up on this. This is guided wave acoustic Brillouin scattering. Here what happens is, other than the longitudinal acoustic modes, you would have some acoustic modes which are, so along the length of the fiber, we had talked about acoustic modes which are propagating along the length. But if I look at the cross section of the fiber, there could be acoustic modes in the angular direction, or there could be acoustic modes in the radial direction, right? Because of this, there could be some amount of Brillouin scattering happening in the forward direction. The frequency, that's first of all very, very weak, and the frequency content looks very different, but that can cause, that could be a source of noise in case of in forward Brillouin scattering, and in especially phase noise. And in coherent communication, that is considered to be one of the limiting features, limiting fundamental source of noise in coherent communication, right? Saurav, optical fiber technology is a digital communication system, which is why we talked about on-off keying and QPSK and 16 QAM and so on. If you have any other questions, let me know. If not, I will move on to the discussion with the assignment. So the question one of the assignment was this. So the first question was to find out the SRS threshold. So that's based on the formula that was given in the class. P threshold is 16 times A effective divided by GR. The key is you have to find out the effective length, and this L effective is 1 minus e power minus alpha L divided by alpha, and you cannot approximate this as always 1 by alpha for all lengths of fiber. This is equal to 1 by alpha only for very long fiber lengths, but when you consider shorter lengths of fiber, you cannot do this approximation. So you have to actually calculate this and find out. In SBS threshold, the relation is, so this is for SRS threshold. In SBS threshold, the relation is slightly modified. We did not derive this, but then let's just use this because that's going to help us find out the basic power levels of operation. So the formula is actually the same, but instead of 16, it becomes 21. That's all, right? So the first two questions are very straightforward. The third question was about the strength of SPM as dash times that of XPM. This is again not very complicated because this is something again we derived in class when we derived from first principles what is cross-phase modulation. At that time, we made this observation about the strength of cross-phase modulation. So it is a kind of lecture material, directly from the lecture material. The next question is about, so there's a calculate the threshold power of a SBS link. So this is question 1, 2, 3 is over. Question 4 is 50 kilo. So length is given 50 kilometer. So length is the information we have. And effective area is given. So this effective area for this problem, as I mentioned earlier, please use 50 micrometer square, because standard single mode fiber at 1550 nanometer, it is 50 micrometer square. GB is given, and you are asked to calculate for two different wavelengths, 1.3 micron and 1.55 micron. The loss is different. The loss is alpha is 0.5 dB per kilometer here, and here it is 0.2 dB per kilometer. So this is a question to kind of ask ourselves which communication, which wavelength is better as far as the nonlinear Brillouin threshold is considered, whether transmission in 1.3 micron is better or 1.5 micron is better. So turns out that the alpha is 0.5 larger for 1.3 micron, and you will see that correspondingly the effective length becomes smaller. And effective length becomes smaller, it means that the threshold becomes larger. So turns out that it is always better to use 1550 nanometer because the loss is smaller, so the effective length is longer, and the longer the effective length, smaller is the threshold. One more difference you can think of is the effective area. The effective area is actually the mode area that should be different for 1.3 and 1.5 micron. But the question I'm saying that if you ignore that difference, just ignore that difference, and then you can calculate. So if you were to strictly compare the SPS threshold for both these wavelengths, you have to actually look at the ratio of effective length area to effective length. That will give you a true picture. But for simplicity, I've asked you to calculate only with respect to the effective length. So that was the next question. Let's move on to the sixth question. This is about coupler. So 4 and 5 was different colors, different wavelengths. Now sixth question is for a directional coupler design, and there were a couple of doubts regarding this question. So you want to achieve, so we know that in a directional coupler you have two fibers which are very close to each other, and they are fused together, and their cores are brought very close to each other, and this arrangement is characterized by a coupling coefficient kappa, and that is given to be 2 meter inverse in the question. The question is, what is the minimum coupling length required for two different coupling ratios? So first is a coupling ratio of 50-50, and the next question is a coupling ratio of 75-25. Now, even though I say minimum coupling length, you have to actually choose from the options given. So it is minimum coupling length from the options that are given, right? So because we know that in the class we derived that the directional coupler which has port 1, port 2, port 3 and port 4, we know port 3 has P1 cos square kappa z, and port 4 has power P1 sine square kappa z. Kappa is given to you. All what you need to do is to substitute the value of z, which gives you this coupling power ratio, rather than inverting and calculating. Because in especially question 7, I think you get some the shortest length need not. Somebody was pointing out in the course that in the forum that it is pi by 12, and I don't see the option pi by 12. Well, you may not. You have to pick the value from the options. So, for example, if you want to have 75-25, there are certain z values that are given. You can substitute in these relations and find out what is the coupling ratio for each of those cases, and pick. It's mostly picking from the given options. Okay, so that is the next one. The next question. Let me move on to question 8. Question 8, which of the following components can be used as WDM demultiplexer to extract single channel. Now, that's again a direct question. When you've gone through the lectures, you will know the answer. Okay, so that's something that is very direct. The next one is, which combination is used as an add-drop multiplexer? Again, this we discussed in detail about using a combination of two such elements as an add-drop multiplexer. So you have to go through the video. I cannot give you the answer, to be directly giveaway. The next question, which is question so 8, 9, refer to the lectures. So extremely simple ones. 10 is a very interesting one. This is more towards how to decide whether any transfer function is possible or not. So let's say, it is impossible, so there's a statement that is given. It is impossible to devise that combines power from two input ports to a third port without loss for a given scattering matrix. Now, scattering matrix is nothing but the transfer function. So you are given a transfer function which gives you, so obviously this is a 3-input port, 3-input, 3-output device. So whatever scattering matrix means, it's a borrowed terminology, borrowed from RF. This is just the transfer function. Now, for example, for a 2x2 coupler, we found the transfer function as 1/√2 1j j1. Okay. Now, it is given that the scattering matrix or the transfer function is 0, 0, S13, 0, 0, S23, S31, S32, S33. So this is a 2x2 device because there are two elements. This is obviously a 3x3 device, right? Which means that there are 3 inputs. Whatever this device does, there are 3 outputs. And the relation that connects the input to output is given by this scattering function or this transfer function. The question says that it is not possible to build a device that will have this kind of scattering matrix because it cannot satisfy energy condition, it cannot satisfy phase matching condition, it scatters from all ports, it causes damage. So, so the key here is for whatever energy you are going in, it has to come out of the device if it is not lossy. Okay, so if it is to satisfy energy transfer condition, this result is slightly from linear algebra, which says that S transpose S conjugate is equal to I. Right. So if this condition is satisfied, then this energy conservation is satisfied. The transformation is what we call as Hermitian symmetry. The transformation has Hermitian symmetry, and hence you will have if this condition is if this condition is satisfied, then it becomes actually a unitary transformation. And if it's a unitary transformation, then the energy conservation is satisfied. So essentially, you're checking whether this condition is satisfied. You can check for example, this matrix. You can check this condition for this transfer matrix. You will realize that it becomes an identity matrix. So that is allowed. Now, the reason why this is not allowed is because when you do this, try to work out this condition, your energy conservation is not satisfied. You cannot produce more energy than what you sent in. Hence, whenever you are developing a device, you have to basically check whether it is satisfying this condition for unitary transformation. Okay, so that is about the next question. Um, the next one is a question on switch. So this again, somebody told me that it is not taught in the class, but you can use the concepts that are taught in the class to actually calculate the answer for this question. So let me explain here. So there is a 4 by 4 switch. Now, what is a switch? A switch is a extension of directional coupler. In a directional coupler, you had two input devices. So this is a 2 by 2 switch. Let me just first explain a 2 by 2 switch. You give a particular power P1 at the input. In a directional coupler, you know that depending on the coupling ratio, you could have power in port 2, sorry, this is port 2, in port 3 or port 4, depending on the coupling ratio and the length of the coupler. Now in a switch, what you do is you keep the length constant, but you keep the coupling ratio variable. Now how do you vary the coupling ratio? There are different methods to do that. We did not discuss those details, but one simple way of doing this is to make an electro-optic material here. So you can change the phase, and hence you can change the port to which the output appears. So the output can appear directly in this bar port, or the output, provided you are giving input here, or it can appear in the cross port, depending on a voltage that you apply on the switch. Right? Now, how do you make this into a 4 by 4 switch? So you can keep cascading this, and that is what is shown in the diagram. So you have one switch, you get two outputs. Now that output you further give to two more switches, and you can keep cascading, and you can build a 4 by 4 switch using 16 2 by 2 switches. That's one way of doing it. Now, what is the crosstalk suppression ratio of 50 dB is given. So each switch has a crosstalk of suppression of 50 dB. What does this mean? When your power is appearing in port 3, the power in port 4 is less than 50 dB corresponding to the power in port 3. That's a crosstalk suppression, because in a switch, whenever the power is appearing in, let's say, port 3, you don't want any power in port 4. Let's say you applied a voltage so that the power appeared in port 3. You do not want the power to appear in port 4. And the crosstalk defines power in port 4 divided by power in port 3 minus 10 log of that. And that is 50 dB, which means that the ratio of the two powers is less than 10 power minus 5. Now, the question is, if I make a 4 by 4 switch using 16 such switches, and if each switch has a crosstalk of 50 dB, what is the overall crosstalk of 4 by 4 switch? So the answer is actually quite straightforward. It means that the input power from, as we discussed, this is less than 50 dB means 10 power minus 5. If P3 is, P4 is less than 10 power minus 5 times P3. That's what this means, right? 50 dB. In a 4 by 4 switch, now how many unwanted outputs are there? Let's say you had 1, 2, 3. Okay, let me just draw this once again. You had 1, 2, 3, 4, whatever be that complicated switch construction, you had 1, 2, 3, 4 outputs. Okay, so how many unwanted outputs are there? If I am switching from, let's say, this port, and I'm applying a voltage such that it switches to, let's say, this port, there are 1, 2, 3 unwanted ports. In a worst case, we get each of them at the desired output with a relative attenuation of 10 power minus 5. So what should be the crosstalk? So there will be 3 times 10 power minus 5. So there could be 3 outputs which are at 10 power minus 5 times less than. So let me explain. If this is P1 and I want to switch to P3, I could have 10 power minus 5 times P1 appearing here. I could have a 10 power minus 5 times P1 appearing here. I could have a 10 power minus 5 times P1 appearing here, right? That is the desired, that's the undesired out, which means I have 3 times 10 power minus 5 P1 power leaking into the other 3 ports. So what would be the net crosstalk suppression? I originally had 50 dB. From that, I'll have to subtract this one, and that will be my crosstalk suppression. Now, if we want a crosstalk suppression to be 40 dB, what should be the crosstalk suppression for each of them? So it's a same question asked in a different way. Let's say you do this 50 dB minus 10 log of 3 into 10 power minus 5. This is the ratio. This is what you would have for the first question. Now, in the next question, you want this answer to be, if you want this answer to be 40 dB, then you're trying to calculate what is this one. So, sorry, you're trying to calculate what is this one. So it's a same way of, 2 different ways of asking the same thing. The next question is question, I think 13 and 14. So for that, there are there's a figure given for 13 and sorry, there's no figure, sorry. A 2x2 biconical tapered coupler has a 40-60 split ratio. So you have a coupler with 40% P1 and 0.6 P1 appearing here. And the insertion loss is 2.7 dB for the 60% channel and 4.7 dB for 40% channel. This is the insertion loss. Input power is 200. So here again, the question P1 is 200 microwatt instead of 200 milliwatt. Find out the powers P1 and P2. So this is pretty straightforward to answer. The insertion loss is power in this port. So insertion loss, how do you calculate this insertion loss here? Power in P3 divided by power input, or P1 in this case, minus 10 log of this. That's your insertion loss. So that is given to you. So it's very straightforward to calculate the power levels P1 and P2. Now, what is excess loss? Now, excess loss is if you had a, I'll explain not for this problem, I'll explain for a 50-50 coupler. You can do it for this problem. If it is a 50-50 coupler, I would expect that P1 becomes P1 by 2, P1 by 2 here, which means I expect a 3 dB loss. But suppose I measure and find out the loss to be some 4 dB here and 3.8 dB here, it means that there is an excess loss of 0.8 dB here and there is an excess loss of 1 dB here. And that's because of the fact that there is some other loss in the system other than just because of the fact that you split the power. So that's how you go ahead and calculate the excess loss. The next question is 15 and 16. The data is the same. There are 2 periodic filters, one with period F1. So you had a periodic filter with period F1. This is like our Fabry-Perot filter. Another with period F2. So there is another filter whose period is F2. Both are assumed to be integers. The first filter selects frequencies f is equal to mf1. M is an integer. The second one selects frequencies f is equal to mf2. Now, if these two filters are cascaded and the resulting function is periodic with the period given by dash. So this is again something like an algebra. Suppose you are cascading these two, you can put numbers like let's say this is f1, this is 2f1, this is 3f1, this is 4f1, and so on. This is at f2, this is at 2f2, this is at 3f2, and so on. Now you can imagine if these two filters, filter 1 and filter 2, this is filter with FSR F1, this is filter with FSR F2. If you cascade them, for example, if you take a frequency 3F1, that is allowed by first filter, but that's not allowed by the second filter. If you take 3F2, for instance, it's not even allowed by the first filter, it won't reach the second filter. So you can find out, but a certain frequencies at which both of them are transmitting, and it is a question of only algebra to find out what is that frequency at which both of them are transmitting. The next question is related to the previous one. If the period is, this is 500 gigahertz and this is 600 gigahertz, then the cascaded structure will be periodic with a period. So if you had calculated the solution for the first one, the second one is just a numerical example of that. Next is question 11. Obviously, I'll give out the answer here. I mean, if you have to get, so what do I demand? I demand that m times f1 must be equal to some n times f2. Right? That's what I would demand. Some where m is an integer, n is an integer, so that at these frequencies the cascade will work as a filter and it will allow that particular frequency. Right? Now, how do you find two numbers such that the smallest numbers or the numbers such that mf1 matches with nf2? The answer is, if you can find out the smallest number is, I mean, this is something that you have learned in your high school also. You would have done this problem. If one number is periodic with period f1, the second number is periodic with period f2. I have a sequence with periodicity. Basically have arithmetic progression with periodicity, common difference is f1. I have another arithmetic progression, common difference f2. The multiplication of this will have a common difference which corresponds to LCM of f1 and f2. You can prove that. Okay, let's move on to the next question. The next question is based on the figure that is given, and the figure tells you that there is a power Pi. It goes through the isolator, and then you have a coupler here, and there is a reflector which is R1 is 0. Then there is a fiber. Here again, the fiber loss is 0.25 dB per kilometer rather than 0.5 dB per kilometer. And then there is a R2, and then there is an isolator here again, and then there is a P0. The question is, optical power launched into fiber through this coupler. This is given to be 1 milliwatt. Coupler has 10 dB power coupling ratio, 1090 coupler. It has no excess loss. So 90% of power is going here. 10% of the power is going here. Refractive index of the core is 1.5. Fiber pigtail, so this is 1.5. The fiber pigtail at port C, so there is no reflection here, which means that all the power that goes through just goes through. Whereas here there is a reflection, which means that there is some power that gets reflected back, and that power will transmit through the coupler back to the isolator and reach here. So neglecting the losses, what is the output power? P0. So what is the path taken by the output power? It goes through this. It cross couples here. 90% of this goes through this fiber. Then a part of it gets reflected. You can calculate from the Fresnel reflection coefficient as to what is that part that gets reflected. It goes back to this and reaches beyond. So on the way, you have to consider the loss of the isolator, the loss of coupling loss, if there's an excess loss, fiber loss, reflection loss, again fiber loss, again coupling loss, and again this isolator loss. So it's a question of calculating the reflection coefficient multiplied by, so the reflection, so input power multiplied by 90 by 100, because 90% goes through this, multiplied by the reflection coefficient, the power reflection coefficient, the fraction that comes back, multiplied by 10 by 900, because from this port, it's only 10% that will get into that. That will be the power. And I think the isolators are considered to be lossless. So you don't have to really consider the loss of the isolator. So this number will give you the power here. Now, if there is a loss in the fiber, obviously you have to take care of that loss along this path. So that is the last question. So that completes this assignment. It's a fairly simple assignment, all mostly based on the formulae. I hope you'll be able to handle it. There's a question here. SPS and SRS threshold is high for 1310 and 1550. So 1310 is better. That is right. 1310 is better than 1550. That is right. I, by mistake, mentioned that it is 1550 better. It is 1310 better in that context. But as I said, what is to be considered here is this ratio, A effective by L effective. We have to go back and calculate what that ratio is to exactly identify which one is better. Larger the threshold, the better for us as far as Brillouin scattering and Raman scattering is concerned. Please ask if you have any further questions. Let me also check the forum or the feedback form, whether there is any other question there. Well, I don't see any responses. In the feedback form. In terms of four-way mixing, XPM, SPM 1550 may be better because zero dispersion, phase matching, nonlinear process can occur easily. That is absolutely right, because if you are working at 1310 nanometer, it will be at zero dispersion. In terms of SPM and XPM, dispersion does not matter because SPM and XPM does not require phase matching. So any nonlinear process which requires phase matching, which is, for instance, four-way mixing, that will happen with very good efficiency at 1310 nanometer because of the zero dispersion at 1310 nanometer. But SPM is an effect which does not require phase matching. So even cross-phase modulation does not require any phase matching because you see the effect is only because of the fact that the power is fluctuating. You have a dP by dt, and that will happen irrespective of what the dispersion is. Well, what can happen is because of dispersion, the pulse get broadened, and instead of very sharp variations, if you have a slow variation, obviously your dp by dt will start reducing. So there's an indirect effect on SPM and XPM due to dispersion, but it does not require any phase matching. So SPM, XPM does not require phase matching. So that effect is the same for 1310 and 1550. Four-way mixing is weakened in the presence of dispersion. That is true. So it is better to operate at 1550 nanometer in that context. Any other questions? Please type in your chat window if there are other questions. Mahesh, looks like there are no more questions. So then we can wind up this session. If you have any more questions, please put it up in the course discussion forum. Thank you.